So some of you may be familiar with my work in the Rust community, such as the static assertions crate, or recently I published a benchmarking library called Divan that I'm quite proud of. And today I will express some of the ways that I've learned how publishing Rust libraries can come with its own interesting challenges. And so I'm mostly going to be focused on libraries. When we say crate, it can also refer to the actual final program executable, but when we're talking about downloading crates from crates.io, we're usually referring to libraries. And so when we talk about libraries and software, we're usually referring to open source libraries, open source being free as in, for some people, free as in freedom, and then for other people, free as in free beer. And I find that one of the things that keeps coming up is how we have all these great free resources that are just provided without much monetary feedback. And so something that I'm asking all of you, if you can, find the libraries that you find most useful and see if you can donate to them. And I think that'll just raise the quality across the ecosystem if we can make that happen. And so libraries as a public good, I think, are one of the fundamental aspects of our industry. And so this is why I think it's important to be careful about how you design the facade, or as we call it, the application programming interface. And Rust comes with its own interesting challenges with APIs. In particular, we have this notion of the borrow checker, where you can either choose to retain a reference to data that the compiler is able to say, oh, yes, this is valid for this scope. And in the case of mutual exclusion with mutable references, the compiler will also say, oh, no, you can't touch that while this other person is updating this value. And there's a few exceptions to that, but generally that's the case. And so when we talk about borrowing versus ownership, I think the main example that ends up coming up is slices versus vectors. And syntactically, that looks like this, which is this bracketed T with the ampersand for slices. The ampersand meaning that this is a reference to some place in memory, and bracketed T being the slice type itself, which is to say, not only is this a place in memory, but this is this number of elements in memory. And vec is very similar, except not only are you saying this is a reference to a place in memory, but you're saying that I can actually take things out of memory there, I can place things there, and as long as I'm the only person who can do that, then that's totally fine. And Rust enforces this. And so when it comes to designing between these two different types, there's various considerations and circumstances we need to consider. So for example, in the embedded world, we're not really going to want to allocate it much. We're going to want to take more advantage of stack. And so you're probably not going to see vec very often. Whereas if you're writing a web server where you have plenty of memory and it's already going to be much faster than Node.js, the CPU compute's not even the bottleneck anyway, just use vec everywhere, why not? And so when you're writing your final binary, there's very different considerations here as opposed to when you're designing a library, because the choices you make here are fairly set in stone for a bit, depending on how upset you want your users to be. And so more often than slices and vec, we actually come across string, because one of the main things we decide computers need to do is process text. And string, or stir versus string, which is an interesting naming convention. I don't agree with it, but on the topic of API design, this is what the standard library has decided. And so I think there's a really good lesson here as a bit of a tangent that even though some people may think there are better names, the fact that we're sticking to 1.0 for as long as possible is phenomenal, so I'm fine with this issue. But anyway, when it comes to stir versus string, you're going to have various operations that aren't going to be usually needing to mutate the data. And so there's a lot of cases where I come across APIs where they're taking as a parameter to a function an allocated string or something that implements into string, when they could have just taken a string slice, and maybe in some paths they end up allocated, but then we have another type called cow, which is beautifully named for copy on write, which can actually be either a stir or a string. However, I feel like cow is a bit unwieldy to use. So there's all these different trade-offs when it comes to designing APIs of whether you want references that you either own the data of, that are shared, mutably borrowed, et cetera, et cetera. Another part of API design that I find interesting when it comes to Rust is metaprogramming. In this case, I'm referring to generic types, generic constants, macros, and build scripts. There's a lot of interesting, powerful things you can do with that. I actually just recently, a few weeks ago, had the fortune of speaking at RustConf on how powerful is const, and the answer is very powerful. I'm very happy with where Rust metaprogramming is today. However, I find that there are some cases where people see that there's these shiny, complex features, and then they insist, oh, well, we're writing Rust, we're smart, we need to be using these features, when you have just much simpler concepts available. So I'll get a bit more into that later. But one of my favorite parts of Rust metaprogramming is its macro system. So you may be familiar with declarative and procedural macros. Declarative macros being ones that you can just write directly in Rust code, saying macro rules, and macros do rule, by the way. And then define certain lexical patterns to accept and be able to perform operations that are very similar to regex. It's a really nice design. And so that's really great for small utilities here and there, or even larger projects that you want to hide away really weird abstractions. So for example, my static assertions crate is just all macro rules, declarative macros. And if it weren't that way, I don't think anyone would use this library. And so the way that I can abstract all these interesting uses of the Rust compiler with macros, I find to be a very lovely and powerful feature of the language. And so I think that more APIs should be using them. They're not very easy to learn, unfortunately, but that's, I think, an opportunity for more of you to come out with blog posts or maybe even books on how to do these specific parts properly. I do recommend the Little Book of Rust Macros. In particular, that's for the declarative macros, macro rules. As far as procedural macros are concerned, I find that David Tolnay has a lot of good resources on that. And you may be familiar with his work, such as the Serity library, serialization and deserialization. It's the go-to library for that in Rust. And when it comes to deciding, do we want declarative or procedural macros, they can be a lot more powerful. The main difference is that with procedural macros, you're writing actual Rust code to parse and expand into other Rust code. Or it doesn't even have to be Rust code. There's some macros that parse Python code and do really weird things with that. And so I find that the flexibility that the APIs that people provide, such as the Serity crate, it's definitely one of Rust's superpowers, and I think that's a great source of inspiration in this area. The other metaprogramming feature of Rust that I find I'm just constantly happy with is the trait system. Now we will have impl traits in traits, which is very meta, and I'm very much looking forward to that. So thank you so much for the people who worked to make that possible. And traits are a very powerful feature of Rust, but I find that some people will confuse their requirements. They'll think that a situation that really needs to express a data format should be expressed in the form of traits, where I find that traits are more of a way to express actions and behaviors. And so this is where I feel that a trade-off comes into place of, well, you can have traits to define a set of behaviors, or if you have a limited set of cases that you're using, you can also use enums, which in Rust aren't just like C enums, where it's basically just an integer. Enums in Rust can also carry state in the form of payload, where you can then pattern match and extract in very interesting ways the kind of information that you store within enums. So when it comes to traits versus enums, the way that I like to think of this trade-offs is that if you want other people to extend the functionality of your library, then go ahead and use traits. However, if your library is doing a fixed set of things, then an enum may not only lead to a simpler design, but also generally better performance. Another fun part about Rust API design is FFI. Rust is fairly good at FFI as far as C is concerned. It is a bit of a struggle to use with other languages. However, I find that the challenge of expressing APIs from other languages in Rust to be very fun. I've done this for Ruby, Objective-C, and Swift now, and there's a lot of high-level concepts across languages, modern languages, that really make me believe less that Rust is a difficult language to learn, because I find that, especially in these cases where I'm wrapping other languages through FFI, I find that because Rust shares a lot of these same concepts, that if we teach things in, say, oh, let's look at how you would write the equivalent Python code, and let's do that in Rust, I think that that leads to people have a better understanding of how to write Rust. And so FFI APIs, I feel, should also have that same feeling of, if I were to write the same code in Python or Ruby, it would feel just as easy. So generally, that's what I think the ideal FFI API for Rust design should look like. And so another main reason that people use Rust is for its performance. So Rust is generally about as fast or C++ for a lot of problems. And on top of that, it adds safety features that these languages don't have. And I find that many people believe these safety features have a higher performance cost than they really do in reality. Bounds checking two registers is extremely fast. And despite the fact that we're writing a language that we're very proud to say, oh yeah, it's very safe out of the box, I find a lot of people reaching for unsafe without really needing to, because they say, oh, well, I need that extra little performance, so we're gonna put some get unchecked calls here and there. And we're not even going to document why. So please stop. I have written a lot of unsafe but sound and justified code in Rust. Specifically, for example, recently with my benchmarking library, given that that code needs to get out of the way of the function that I'm actually benchmarking, then that means it needs to be basically micro-optimized and have as little of a footprint as possible. And so I feel that that's a case where reaching for unsafe to, for example, initialize a slice of maybe uninit, maybe a valid use case. However, if you are going to reach for unsafe to just eke out the extra little performance that you feel is necessary, please write in big capital text safety and explain why you are deciding to make life harder for your teammates. And I do think that there's a lot of code that the only way to do it properly is unsafe. This is especially the case with FFI. But I find that it leads to just too much risk. And if we're going to abide by like the values that Rust provides us or Rust is built on top of, then let's make sure that our programs behave as expected and the computer's okay. No surprises, please. No undefined behavior. And so if you're going to be using unsafe, you can test it with this absolutely amazing Rust code runner called Miri, which is the mid-level intermediate representation interpreter. It's essentially the representation of Rust that stands between your actual Rust and your LLVM. And so Miri is able to take that representation and analyze the way that it accesses memories or the way that it accesses synchronization, such as atomics being used in the wrong order and telling you that, oh, well, actually, you end up with a data race because you actually can't get away with a relaxed load over here. And so Miri is just very powerful. So if you are going to reach for unsafe, please run Miri, run in CI, and the world will be a better place. So generally in testing, I find that Rust has a very good story here. I find that the way that you register tests in Rust and the way that you run them through Cargo is extremely straightforward and simple, and I really wish that other languages, coming from Swift especially, would do this better. So given that it's so easy to register tests, I don't think there's any excuse to not test our libraries. Even if you're just starting off, do test-driven development and decide, okay, this is the exact behavior that I'm looking for, so let me make sure that my library that does nothing fails that test, because if it passed that test, then you have bigger problems. Another thing that Rust makes really easy is testing your documentation. The same way that you would run your normal tests, you run cargo test, and then there it's able to see the examples that you had listed for people to follow and ensure that what you're telling people to run will actually work. I think that this is a phenomenal feature and should definitely be more utilized. You can also utilize this with your README if you use the include stir macro on your README. So have fun with that. And along with your documentation, I find that an extended form of documentation, how you're using your library, is through examples. Specifically, in the case of Rust, there's an examples directory that you can set. And you can just toss files in there that just use your library exactly how you want people to use them for different scenarios. And so this is much better for demonstrating how you'd write proper applications or end-to-end programs, whereas trying to fit larger, more complex programs within your proper documentation is going to result in a really tiny scroll bar. And so while you're doing all of these good behaviors, you should also be automatically doing them in CI. You should be ensuring that when someone contributes to your project, that you don't need to trust it on blind faith, that it's not going to break anything. Also, Rust makes it very easy to support multiple platforms. So CI is a great opportunity to ensure that if you're doing platform-specific code, that it actually does work for that platform. And so I think especially today with how easy GitHub Actions is, this is another area that I find lacking, that there's not really much justification to not be running, especially for libraries, your tests in CI. And so we've done all of these good behaviors while developing our library. And so now we decide, OK, well, I'm pretty happy with my API, so let me go and run cargo publish. And it's great that you get to this point. Not a lot of people do, because I find that's often the case. Many people end up getting fixated on having the perfect API, all the features that this competing library has. And that's very much not needed or expected by the community for an initial version of a library. I think having something that is different but still very valuable is much better than having nothing at all, even if it's missing the features that you want as an author. These can always be added later, and also at a later point, you may even have a better intuition on how to implement it than you did initially when you first tried publishing your library. And while you're publishing your library, please tag the commit with Git. It makes it so much easier for various tools to track your versions, and websites like GitHub allow you to display diffs between tags. And so while you're writing your changes, you can also tell people, hey, this is the exact code that changed, and link to that. So I find that Git tags are a small but still very powerful feature that still too many, especially big library maintainers, don't use. And I find that to be very annoying and also not very justifiable. So fundamentally, to publishing a crate within the Rust ecosystem is semantic versioning. This is how we decide that one version of a library can be compatible with another. And the format that it takes is just 3 digits, where the red one, the X, is the major version. This is essentially saying that, oh, something big has changed in this library, so we're updating that, and it becomes instantly uncompatible. Then we have the Y, which is the minor version, and that's essentially for new features, and people may want to automatically update to that. Finally, we have Z, which is just bug fixes. And so when you publish an initial version of a library, maybe you want to do 1.0, or maybe, in particular in the Rust ecosystem, you'd want to do a 0.1. And the reason I recommend a 0.1 versus a 1.0 is that it instantly tells your audience that this thing is still being actively developed. And the rules for 0.1 and 1.0 end up being pretty similar to each other, but just shift by 1 digit. So if the blue 0 at the end ends up changing, then that's essentially the same as adding a feature. But if that green 1 changes or that red 0 changes, then that means it's going to be a breaking change. You can also use a 0.0, which anyone know the difference between 0.0 and 0.1 as far as how semantic version applies to them? There is no difference. Same exact rules apply, just think of that 1 as a 0. And so checking semantic versioning is really hard in Rust, in particular Rust, because it has so many complex features. So there's this really amazing tool called Cargo Semver Checks that I highly recommend you try and use in your projects. It will automatically check Cargo Semver violations between different versions of your crate. And the way it works is using this really powerful query engine called TrustFall, where it's analyzing the rust.json and essentially getting all the type and API information from there. If you have not heard of TrustFall, if not talked your ear off about it yet, then please see me. But it's a query engine where, if you think of foreign data wrappers in Postgres, imagine the inverse of Postgres in that situation, where foreign data wrappers are kind of an add-on feature, whereas this is the fundamental feature. So it's not a database in itself, it's querying other data. Another consideration when it comes to publishing is your minimum supported Rust version. This has caused a lot of contention in the Rust community, and I understand both arguments of deciding not to support that changing the Rust version of your library is a breaking change. But at the same time, there's a lot of package managers that are on older Rust versions where if a change to a library requires updating the Rust version, you're going to be inconveniencing a lot of people who will actually really want to use your library. So if you decide on a policy of whether it's a breaking change or not, please state that in your README and your documentation, and hopefully people understand your stance either way. After publishing, you still have more work to do. You need to maintain the library. No, you can't get away that easily. You can't just hit publish and walk away, although some people try. And this is a very huge burden. A lot of the people who use the open source library ecosystem don't recognize that this amount of work that comes with it, especially for free, just doesn't really make sense unless it's a project that someone's really passionate about. I've known many people who have burnt out from being in the open source ecosystem where initially they just were in love with their project but decided that, oh, well, this is too much extra work beyond my day job. But if we decide, okay, well, we're going to be good stewards and actually maintain our project, then one of the first things that you should be adding to your project is a changelog. This is essentially what it sounds like, where you can track and list various versions across your project and what has changed between those versions. Going back to Git tags, this is a great place to link those Git tags and link the GitHub diff between those tags. And if you want people to help you with your project and not just use it, tell people and enable them to do so. I think that this is an easy but often missed way of reducing the burden on open source maintainers. And if you can't contribute financially to a project, then consider finding a low-hanging fruit feature or bug and becoming the person who can fix that and become a contributor. So that is everything that came to mind when it comes to publishing high-quality crates. Thank you for coming out here. You can follow me on Mastodon at Hachyderm. I'm Nikolai on there. Twitter is Nikolai Vazquez, my full name. I've been very excited with my benchmarking library, Devon, so please check that out. I very much take my own advice from this talk, where good is not, doesn't have to be the enemy of perfect. So lots of progress to be seen there. And definitely do check out Trustfall. Predrag Grevsky and I are building really interesting things with that. So very happy to discuss that further.